Welcome back to Math 103. This is video number 8 on apportionment. We were comparing the Hamilton apportionments for 37 seats and 38 seats in our latest version of our favorite recurring example, and what do we notice? So we notice that Massachusetts gains a seat, Connecticut gains a seat, and Maine loses a seat. Oh my, that is very astonishing. Right, that is bizarre. That doesn't seem to make any sense. Because you had your apportionment, all you did was add one seat, and you would have thought that one state would get the extra seat, and all the rest would stay the same. That would have made sense. What you have just witnessed is the Alabama paradox. We have just observed an instance of the Alabama paradox. Increasing the number of seats and changing nothing else about the apportionment problem, just adding a seat, can cause a state to lose seats. In this case, it was Maine that lost out. So to stop and think for a moment, does this scenario remind you of the violation of a certain fairness criterion of voting? I claim that this is reminiscent of the monotonicity criterion. Right? An occurrence of the Alabama paradox in the setting of apportionment is reminiscent of a violation of the monotonicity criterion when we're talking about voting methods. Why does that make sense? What is the connection there? Well, in both cases, you're doing something that's supposed to help someone, or at least not harm anyone, and it ends up harming someone. And that doesn't make any sense. It makes you think that the voting method has something irrational about it, and it makes you think that the apportionment method has something irrational about it. This is one of the flaws of Hamilton's method. It is vulnerable to the Alabama paradox. So the good news is that it always respects the quota rule. The bad news is that it sometimes gives rise to the Alabama paradox. In fact, it was a specific instance of the Alabama paradox that led to Hamilton's method being thrown out as the official apportionment method for the U.S. Congress. What have we done so far? We've defined the apportionment problem, we've thought about how to set it up and make sense out of it, we even have a method for solving it, Hamilton's method, and we've seen some of the advantages and disadvantages of that method. So there is another approach, another general approach to solving the apportionment problem that we're really going to need to understand. And this other approach is going to lead to Hamilton's method, but it's also going to lead to important variations on Hamilton's method, all of which have been used in practice in American history to apportion Congress. At the beginning of every apportionment problem, we can ask the following warm-up question. We can ask, what is the average population per seat overall? In other words, if every congressional district had exactly the same population, what would that population be? Now, to be clear, we're talking about every congressional district across the entire country, not just inside each state. So for sure, inside each state, the boundaries are supposed to be drawn so that there's the same population, or very nearly the same population, in each district. But from one state to the next, as we saw when we contrasted New Hampshire and Rhode Island before, from one state to the next, we can find in practice that the number of people living in each district is quite different state to state. So suppose ideally that every congressional district actually had the same population from state to state. What would that population be? So we can answer that question for our Red Sox territory example, the original version with 25 seats. Let's think about that. What would the population of each district be if they all had the same population? The average population per seat is the total population divided by the number of seats. Okay. And that equals 13.9 million divided by 25 seats, and that works out to be 556,000 people per seat. Okay, notice the units here, people per seat. The average population per seat is 556,000 people per seat. In other words, if every congressional district had the same number of people, they'd each have 556,000 of them. This is an important quantity. We give a special name to this special quantity, the average population per seat, or the ideal population of a congressional district, if they all truly had the same population. We call this the standard divisor. So the standard divisor equals the total population divided by the number of seats. That's what we just computed. And we think average population per seat, or we think population of a standard-sized congressional district. To practice this idea of standard divisor, let's compute another one. So before going on to the next video, answer the following two questions. So we've looked at a variation of our example in which there are only 21 seats instead of 25. We did that earlier. So without computing it, or before you even compute it, just by reasoning, do you think that with only 21 seats instead of 25, with only 21 seats, will that make the standard divisor greater than or less than it would have been if we'd stuck with the original 25? Right? Does fewer seats mean a greater standard divisor or a smaller standard divisor? So think about that first, try to reason that out, and then actually compute it. Compute the standard divisor when you have 21 seats and the total population is still 13.9 million.